It's 2:43 inches, the quiet hours of the morning in Baltimore, Maryland. Inside the Space Telescope Science Institute, the entire building is still. Most of the staff left hours ago, but one planetary scientist remains at her workstation, her eyes fixed on her screen. She stayed late tonight, anticipating the arrival of crucial data. The James Webb Space Telescope, the most sophisticated observatory humanity has ever built, has been collecting spectral data for Uranus. The data pipeline was expected to finish processing soon, but unexpectedly, it's ahead of schedule. The team was expecting a delay, but here it is, data that no one could have predicted. When the information finally loads onto her screen, she feels a jolt of excitement. This is not a photograph. It's far more than that. It's a three-dimensional map, a map that shows the vertical portrait of Uranus's atmosphere, stretching an astonishing 5,000 kilometers above the planet's cloud tops. And for the first time in the history of planetary science, the map doesn't just show the surface, it reveals depth, complexity, and intricate details that no one thought possible. With a sense of awe, she runs the temperature profile. She stops reviewing the result. Then she runs it again, trying to ensure she's not missing something. The temperature and ion density peaks are at two completely different altitudes, separated by thousands of kilometers of atmosphere. These two key phenomena are operating independently in two distinct regions at the same time. Every atmospheric model that's been constructed up to this point says this should not be possible, not on this planet. And yet, here it is, staring her in the face. She takes a breath, pulls up the 30-year cooling record, and runs the numbers again. The trend is still there, the cooling process is ongoing, and no one has ever been able to explain it. The data is both startling and unsettling. For 30 years, the scientific community has trusted models to describe the behavior of Uranus's atmosphere. But this data doesn't fit into any model. It doesn't follow the rules that have governed our understanding of planetary atmospheres. With a quiet sense of unease, she types 4 words into the team message thread: "We need to talk tomorrow." The data has revealed something that will change everything they thought they knew about Uranus. A planet that, for years, had been regarded as cold, featureless, and scientifically unremarkable. Uranus is no longer just a frozen gas giant. What the James Webb Space Telescope has shown us is the complete dismantling of everything that textbooks taught us about this distant planet. But this is just the beginning. The real weight of these findings lies in the broader implications they hold. This data isn't just a question about one planet. It's a challenge to our understanding of planetary physics. What Webb has revealed challenges the very framework we've used to describe the most common type of planet in the entire Milky Way galaxy. This is not just an isolated anomaly. It's a fundamental rift in how we think about planets, their atmospheres, and the forces that shape them. To understand the full weight of this discovery, we need to go back in time, to the last time humanity got a close look at Uranus, the last time we truly examined it. That brief, historic moment will help us understand just how much things have changed since. The year is 1986, January 24th. NASA's Voyager 2 spacecraft, having already completed historic flybys of Jupiter and Saturn, embarks on its final approach to the 7th planet Uranus. Voyager 2 was on a trajectory that was calculated to exploit a rare planetary alignment, one that occurs only once every 176 years. The spacecraft's approach to Uranus was brief but groundbreaking. Its instruments measured Uranus's basic physical parameters with precision that no Earth-based telescope could ever achieve. Voyager 2's encounter, although short, gave us the first and only close-up look at this ice giant. At the time, what it found seemed to confirm the scientific consensus. Uranus was a cold, unremarkable world. The upper atmosphere of Uranus registered temperatures of -224 degrees Celsius, the coldest planetary atmosphere in the entire solar system. This fact alone should have raised more questions than it did. After all, Uranus is farther from the Sun than Neptune, and yet it was colder than Neptune, a planetary anomaly that deserved more attention. But the broader picture painted by Voyager 2 was of a world in thermal equilibrium, slowly radiating the small amount of energy it received from the Sun. This image of a stable, quiet world persisted for years, and scientists had no reason to doubt it. That is, until the early 1990s, when something strange began happening. Ground-based observatories that were monitoring Uranus started noticing an odd trend in the planet's upper atmosphere. For reasons that no one could explain, the atmosphere was cooling continuously, year after year, with no sign of stopping. It wasn't fluctuating, it wasn't going through seasonal shifts, it was just cooling. The cooling anomaly was confirmed through independent observational campaigns. Yet, there was no explanation. No one could figure out what was causing the upper atmosphere to lose heat. For decades, scientists were left with an unresolved mystery that no one could solve. The question remained, what was draining heat from Uranus's atmosphere? And so, the mystery persisted. Uranus had become a cold case in planetary science, a case no one could solve, not because they weren't trying, but because Uranus was simply too far away, its emissions too faint, and its atmosphere too complex for any existing instruments to study in detail. What scientists didn't know at the time was that the answer would come from an observatory far more advanced than anything that had ever come before. In 2021, the arrival of the James Webb Space Telescope ushered in a new era of space exploration, one that would challenge every assumption about distant planets. Webb is not just a telescope, it's a marvel of engineering. Unlike any instrument before it, Webb is designed to capture infrared radiation with unparalleled precision. Its primary mirror spans 6.5 meters in diameter, nearly 3 times the size of Hubble's, and is composed of 18 hexagonal gold-coated beryllium segments. Webb's position, 1.5 million kilometers away from Earth at the second Lagrange point, L2, allows it to avoid Earth's thermal emissions, making it the perfect tool for observing faint cosmic signals. It is capable of detecting thermal emissions so faint that they were invisible to any other telescope before it. When Webb turned its powerful gaze toward Uranus, the scientific community was buzzing with anticipation. Webb's ability to detect infrared light would allow astronomers to peer deeper into Uranus's atmosphere than ever before. For 15 continuous hours, the telescope observed Uranus's upper atmosphere using a specialized instrument called NIRSPEC, the near-infrared spectrograph. Unlike traditional imaging, NIRSPEC collects spectral data across a two-dimensional field, producing a data cube that contains a full spectrum at every spatial position. This allowed the scientists to obtain crucial details about the planet's atmosphere, temperature, chemical composition, particle density, and velocity all at once. The data collected by Webb was revolutionary. It didn't just offer a snapshot of Uranus, it gave the team the first true three-dimensional map of the planet's upper atmosphere. They could now see Uranus in a way that had never been possible. For the first time, scientists could observe the planet's atmospheric layers from just above the cloud tops all the way up to 5,000 kilometers into its ionosphere, the charged upper layer where solar wind and magnetic fields interact. As the team pored over the data, it became clear that this map wasn't just an ordinary representation of the planet, It was a window into a much more complex and dynamic world than anyone had expected. The previously identified cooling trend was no longer just a mysterious anomaly. It was part of a larger, more intricate picture, one that Webb had just begun to reveal. What Webb's data uncovered was more than just a revelation. It was a puzzle that no one had anticipated. For years, scientists had assumed Uranus's upper atmosphere was uniformly cold, averaging a frigid negative 224 degrees Celsius, but Webb's three-dimensional temperature profile told a completely different story. The temperature at the lower altitudes was indeed as cold as expected, but something unexpected happened as the data went higher. At altitudes between 3,000 and 4,000 kilometers above the cloud tops, the temperature surged to a surprising 150 degrees Celsius, still cold by Earth standards, but a significant increase compared to the negative 224 degrees Celsius measured at lower altitudes. This was a startling finding. Uranus receives only a fraction of the solar energy that Earth does, and the solar flux available to heat its atmosphere is 370 times weaker. Conventional models of atmospheric heating couldn't account for this temperature gradient. The energy from the sun simply isn't enough to explain such an increase in temperature. So, the burning question remained: where was the extra heat coming from? Scientists have long been aware of a phenomenon known as the energy crisis in ice giant atmospheres. Both Uranus and Neptune exhibit temperatures in their upper atmospheres that are much higher than solar radiation can explain. Some theories suggested that the heat could be coming from the planet's magnetic field, wave heating, or particle precipitation from the magnetosphere. However, Webb's data added a new layer to this problem, showing that the planet's upper layers were being heated by something far more complex. What we now know is that Uranus's atmosphere is not just passive, receiving solar energy and radiating it back into space. Instead, something else is actively adding heat to the system, an unknown energy source beyond what the sun can provide. This is a mystery that has baffled scientists for decades and remains unresolved, and Webb's data is the first clear clue pointing to this additional source of energy. The story doesn't stop with the temperature anomalies. Webb's data revealed even more unsettling information about Uranus's atmospheric structure, particularly when it came to the planet's magnetic field. Uranus is unlike any other planet in our solar system in this regard. While Earth's magnetic field is relatively stable, with its rotational and magnetic axes aligned at a small angle, Uranus's field is chaotic and far more complex. Uranus's magnetic field is tilted at an extreme angle, 98 degrees, relative to the planet's orbital plane, and the field itself is offset from the planet's center. As Uranus rotates, its magnetic field doesn't rotate symmetrically like Earth's. Instead, it tumbles and wobbles in a chaotic pattern that makes the planet's magnetosphere behave in a way no other planet's magnetosphere does. This unique magnetic configuration creates irregularities in the ionosphere, leading to complex auroral patterns and temperature variations that have never been seen before. Webb's observations of Uranus's ionosphere revealed two distinct auroral bands located near the planet's predicted magnetic poles, exactly where theoretical models said they should be. However, Webb also detected something that stopped the scientific team in their tracks: a dark region between these two auroras, a visible gap where the atmosphere's glow and ion density were significantly depleted. This dark band was not caused by the absence of atmosphere, but by the planet's magnetic field. It was a magnetic shadow, a direct consequence of Uranus's chaotic and asymmetric magnetic field. In this dark band, the magnetic field lines prevent energetic particles from descending into the atmosphere, blocking them entirely. The result is a region of the ionosphere with little to no auroral emission, a magnetic feature that had never been observed before. This phenomenon explains the temperature anomaly Webb had earlier detected. The irregular magnetic field is pumping energy into Uranus's atmosphere unevenly, creating complex heating patterns at different altitudes. The result? A planet that is far more dynamic and active than anyone had previously realized. Uranus, once thought to be a cold and lifeless planet, is now understood to be far more dynamic. Its atmosphere is not static. It is not just a frozen shell, as Voyager 2's data suggested. Instead, Uranus's upper atmosphere is a complex, ever-changing system driven by a combination of factors: solar radiation, magnetic interactions, and unknown heat sources. These forces work together to create an environment that defies every expectation. What Webb has revealed is the true complexity of this ice giant. It's a world in constant motion, where energy is constantly being transported, where magnetic fields shape the atmosphere in unpredictable ways, and where thermal processes are still at play long after scientists believed they had unraveled the mysteries of this distant planet. Uranus is not a dead world. It is an active, dynamic planet with complex interactions between its magnetic field, atmosphere, and energy sources. And the implications of this discovery extend far beyond Uranus itself. Perhaps the most exciting implication of Webb's findings is how they will shape our understanding of exoplanets. Ice giants like Uranus are not rare in our galaxy. In fact, they are believed to be among the most common types of planets found in the Milky Way. For years, astronomers have been discovering exoplanets that closely resemble Uranus in size and composition, but until now, we had no detailed model to help us understand them. Webb's data has provided the first comprehensive blueprint for studying ice giants. By mapping how energy flows through Uranus's atmosphere, how its magnetic field shapes its ionosphere, and how heat is transported across its atmosphere, Webb has given us the tools to study other exoplanets with similar characteristics. These findings will serve as a baseline for characterizing every ice giant discovered in the future. But Uranus still holds many secrets. The 30-year mystery of its cooling atmosphere is far from solved, and scientists are now planning future missions to study the planet more directly. The next step may involve sending a dedicated probe to Uranus, one that can enter its atmosphere and analyze its complex structure up close. The James Webb Space Telescope has opened the door to a new era of planetary science. Uranus is no longer the cold, featureless world it once appeared to be. It's a dynamic, complex planet, one that holds the key to understanding not just its own history, but the broader forces at play in the universe. And as we look toward the future, the discoveries that await us will continue to reshape our understanding of the cosmos.